Close your eyes now, and let yourself drift into a world of elegant simplicity. Tonight, we journey through the periodic table, that beautiful grid of elements that makes up everything you've ever touched, everything you've ever seen, and everything you are. There's something deeply calming about the periodic table, something that speaks to the most ancient part of our minds. Perhaps it's because these elements represent the ultimate truth of our universe, the fundamental building blocks arranged in perfect, predictable patterns. When we contemplate the periodic table, we're looking at nature's own architecture, and there's a profound peace and understanding that beneath all the chaos of daily life, these patterns hold steady and true. Let us begin our story with hydrogen, the first element, the simplest of all. Hydrogen has just one proton and one electron, the most basic arrangement possible. When you think of hydrogen, imagine the dawn of the universe itself, just moments after the Big Bang, when hydrogen atoms first formed in the cooling cosmic soup. This element makes up about 75% of all ordinary matter in the universe. It is the fuel of stars, the essence of water, the foundation of life itself. There's something meditative about hydrogen's simplicity. One proton, one electron. Nothing more needed. In a world of complexity, hydrogen reminds us that profound importance can come from the simplest forms. As you breathe slowly in and out, consider that every breath you take involves hydrogen atoms bonded to oxygen. The water vapor in your breath, the moisture in your lungs, all contains hydrogen that has existed since the universe began. These same hydrogen atoms have been part of ancient oceans, have fallen as rain on prehistoric forests, have passed through countless living beings before coming to rest, temporarily, in you. This cycling, this eternal journey of elements, has a rhythm to it like a cosmic lullaby. Hydrogen teaches us about beginnings, about simplicity, and about how the smallest things can be the most essential. Move now to helium, the second element, named after Helios, the Greek god of the sun. Helium was actually discovered in the sun before it was found on Earth. In 1868, astronomers noticed a strange yellow spectral line in sunlight during a solar eclipse, a signature that matched no known element. They realized they had found something new, something that existed in the stars before humans knew it existed beneath their feet. Helium has 2 protons and typically 2 neutrons, and it is so stable, so content with itself, that it rarely reacts with anything. It is one of the noble gases, elements so complete unto themselves that they need nothing else. There's a meditative quality to helium's self-sufficiency. It floats, it rises, it escapes even Earth's gravity given enough time. Helium in party balloons eventually seeps through the rubber and drifts up through the atmosphere, past the clouds, past where airplanes fly, all the way to the edge of space where it disperses into the cosmic void. This element cannot be renewed on human timescales. Once it escapes, it's gone forever, returning to the stars from which it came. In this way, helium teaches us about letting go, about the natural tendency of things to return to where they belong. As you feel your body growing heavier, sinking into your bed, imagine helium doing the opposite, becoming lighter, freer, ascending peacefully upward. Now we come to lithium, element 3, the lightest metal. Lithium is soft enough to cut with a butter knife, and when exposed to air, its silvery surface quickly tarnishes to a dull gray. But lithium holds remarkable power. It is used in batteries that power our phones, our computers, our electric vehicles. This soft metal somehow stores and releases energy with remarkable efficiency. Even more fascinating, lithium has been used for decades to help stabilize mood in people with bipolar disorder. Scientists still don't fully understand why this simple element, this third member of the periodic table, can bring such calm to the human mind. Perhaps there's something poetic about that. The same lithium atoms that were forged in the hearts of dying stars billions of years ago now move through human neurons, carrying tiny electrical charges, helping to create balance and peace in consciousness itself. Lithium occurs naturally in small amounts in drinking water. Some studies have suggested that areas with slightly higher natural lithium in the water supply have lower rates of certain mental health problems, though the research remains debated. Regardless, there's something beautiful about the idea that elements from the periodic table, scattered through our environment in trace amounts, interact with our biology in subtle, complex ways we're only beginning to understand. Every element has its role, its purpose, its place in the grand design. As you settle deeper into relaxation, think of lithium as an element of balance, of the soft power that requires no hardness to be effective. Let's move to beryllium, element 4. Beryllium is rare, toxic, and yet utterly essential for certain technologies. It's found in emeralds and aquamarines, giving these gems their beautiful green and blue colors. When you look at an emerald, you're seeing beryllium atoms arranged in a crystalline lattice with chromium, scattering light in that distinctive, treasured way. Beryllium is also used in spacecraft because it's lightweight and strong, and it doesn't deform when temperature changes. Something about beryllium speaks to hidden strength, to the idea that rare things can be precisely what's needed for extraordinary circumstances. Not everything must be common to be valuable. Boron comes next, element 5, sitting at the top of its own group in the periodic table. Boron is essential for plant cell walls, helping them maintain structure and communicate signals about growth. Without boron, plants cannot properly develop. In that way, boron is an element of structure, of framework, of holding things together so that life can flourish. Boron compounds are also found in heat-resistant glass, the kind used in laboratory equipment and kitchen bakeware. When you take a dish from a hot oven, you're trusting in boron's ability to help materials withstand thermal stress without shattering. There's something calming about elements that provide stability, that create the conditions for safety and growth. And now, carbon, element 6, the foundation of organic life. Carbon is unique among elements in its ability to form long, complex chains and rings, bonding with itself and with other elements in an almost infinite variety of ways. Every living thing on Earth is built on a framework of carbon. Your DNA, your proteins, your cells, all are carbon-based structures. The same element forms both the soft graphite in pencils and the hardest natural substance, diamond. Carbon dioxide in your breath feeds plants. Carbon in ancient forests, buried and compressed over millions of years, became the coal and oil that powered the industrial age. Carbon takes so many forms, plays so many roles, connects so many systems. In the periodic table, carbon sits perfectly positioned to bond with almost anything, a social element, endlessly versatile. When you think about carbon, you're thinking about the element that makes you possible. The carbon in your body was forged in stars that exploded long before our sun existed. You are made of stardust, quite literally. Those carbon atoms in your fingertips, in your heart, in your thoughts, were once in the core of a massive star undergoing nuclear fusion, then scattered across space in a supernova explosion, eventually coalescing in the cloud of gas and dust that became our solar system. You carry the history of the cosmos in every cell. This is perhaps the most calming fact of all, that we are not separate from the universe but are the universe experiencing itself, arranged temporarily in this particular pattern of elements. Carbon reminds us of our connection to everything. Nitrogen follows, element 7, making up 78% of the air you breathe. Most of Earth's atmosphere is nitrogen gas, pairs of nitrogen atoms bonded so tightly together that they rarely break apart to react with other elements. This stability makes nitrogen an inert buffer, diluting the oxygen so it doesn't combust everything too rapidly. Nitrogen is also essential for proteins in DNA. All living things need nitrogen, yet most cannot use the nitrogen gas in the air directly. Certain bacteria can fix atmospheric nitrogen, converting it into forms that plants can use. This process, happening in soil and in the nodules of legume roots, is one of the quiet miracles that makes life possible. Nitrogen moves in cycles, from atmosphere to soil to plants to animals and back again, an eternal circulation that has continued for billions of years. There's a gentle rhythm to the nitrogen cycle, like breathing on a planetary scale. As you breathe in now, nitrogen molecules enter your lungs, pass through essentially unchanged, and exit again when you exhale. They witnessed your breath, carried along with oxygen, but remained themselves, stable and inert. These nitrogen molecules might have been breathed by dinosaurs, by ancient humans, by every creature that has ever lived. In this way, nitrogen connects us across time, a shared atmosphere that all Earth's creatures have moved through. Let this thought ease you deeper into rest. Oxygen, element 8, is the breath of life itself. When you inhale, oxygen molecules enter your lungs, diffuse into your blood, bind to hemoglobin, and travel to every cell in your body. There, in the mitochondria, oxygen participates in the process that extracts energy from food, the slow, controlled burning that powers your life. Oxygen makes up about 21% of the atmosphere, a percentage that's just right. Less, and we couldn't sustain complex life. More, and fires would rage uncontrollably. Earth's oxygen comes primarily from photosynthesis, the process by which plants and algae use sunlight to split water molecules, releasing oxygen as a byproduct. The oxygen you're breathing right now was likely produced by a plant or ocean phytoplankton in the past few months or years. Oxygen is highly reactive, eager to bond with other elements. It's what causes iron to rust, apples to brown, fires to burn. Yet this reactivity is also what makes it so useful for life. The controlled reaction between oxygen and nutrients in your cells releases energy gently, in manageable amounts, rather than all at once. Your body is constantly managing this process, this slow burning that keeps you warm and alive. There's something profound about how oxygen, so potentially dangerous in its reactivity, is tamed by biology into the fundamental process of respiration. As you breathe slowly, feel gratitude for oxygen, for the plants that make it, for the billions of years of evolution that learned to harness its power. Fluorine, element 9, is the most reactive element on the periodic table. Fluorine gas is so aggressive that it can make water burn. It will react with almost anything, even gold and platinum. Yet in controlled amounts, fluorine compounds strengthen tooth enamel, helping prevent cavities. The fluoride in toothpaste or drinking water isn't fluorine gas but fluorine bonded to other elements, tamed into a form that can help rather than harm. This speaks to one of the great truths of chemistry: context matters. The same element can be deadly in one form and beneficial in another. Fluorine teaches us about intensity, about power that must be respected and channeled appropriately. Even the most reactive, aggressive forces can serve positive purposes when properly understood and applied. Neon, element 10, brings us to another noble gas. Neon is famous for glowing signs, that distinctive orange-red color when electricity passes through neon gas. Each element, when energized, emits light at specific wavelengths, a unique signature. Neon's glow has illuminated cities, marked theaters and diners, created art from commerce. Neon itself doesn't react with anything under normal circumstances. Like helium, it's complete unto itself, needing nothing. Yet when energized, it shares its inner light with the world. There's something meditative about neon's glow, steady and consistent. The neon in signs today contains atoms that have existed unchanged since before Earth formed, now temporarily borrowed to light our way. When the sign is turned off, the neon returns to darkness, content, stable, eternal. Sodium, element 11, is a soft, silvery metal so reactive that it must be stored in oil to prevent it from reacting with moisture in the air. Drop sodium in water and it reacts violently, sizzling, skating across the surface, sometimes bursting into flame. Yet sodium is essential for life. Sodium ions carry electrical signals in your nerves. Every thought you have, every movement you make, depends on sodium ions flowing across cell membranes, creating the electrical impulses that neurons use to communicate. The sodium in your body came from food, ultimately from salt, sodium chloride, formed when reactive sodium bonded with reactive chlorine to create something stable and essential. This is one of chemistry's miracles, two dangerous elements combining to form something necessary and safe. Magnesium, element 12, sits at the center of chlorophyll, the molecule that makes plants green and captures sunlight for photosynthesis. Every green leaf you've ever seen owes its color to magnesium. This element is also important for your muscles, your bones, hundreds of enzymes in your body. Magnesium has a lightness to it, a certain brightness. When magnesium burns, it produces an intensely bright white light, the kind once used in old camera flashes. Stars use magnesium in their fusion processes, building it from lighter elements. Like so many elements, magnesium connects us to stars, to plants, to the fundamental processes that make worlds possible. As you relax, imagine magnesium in leaves capturing sunlight, that ancient energy arriving from the sun after 8 minutes of travel through space, caught by an element forged in stellar furnaces. Aluminum, element 13, is the most abundant metal in Earth's crust, though for most of human history we couldn't isolate it. Aluminum ore is very stable, requiring large amounts of energy to separate aluminum from oxygen. Once we developed the technology, aluminum became ubiquitous, valued for being lightweight, strong, and resistant to corrosion. A thin layer of aluminum oxide forms instantly on aluminum's surface, protecting the metal beneath. This self-protective quality speaks to resilience, to the ability to meet challenges by adapting. Aluminum foil, aluminum cans, aircraft frames, all leverage this element's useful properties. The aluminum in these objects will outlast us, recyclable essentially forever, never degrading or losing its metallic qualities. There's a permanence to elements that transcends the temporary forms they take. Silicon, element 14, is the foundation of modern technology. The computer or phone you use, the solar panels that harvest sunlight, all depend on silicon's semiconductor properties. Silicon's ability to control the flow of electrons makes digital technology possible. Yet silicon is also the second most abundant element in Earth's crust, present in sand, in quartz, in countless minerals. Beach sand is largely silicon dioxide, tiny crystals worn smooth by waves. This means that the technology that defines our age is built from one of the most common materials on Earth, transformed through human ingenuity into something that can store information, process calculations, connect billions of people. Silicon reminds us that abundance can be as valuable as rarity when we understand how to use what's available. The sand beneath your feet at the beach and the chip in your computer are both silicon, in different arrangements. Context and structure determine function. This principle applies beyond chemistry. How we arrange the basic elements of our lives determines what we create and experience. As you drift closer to sleep, let go of worrying about arrangements. Elements cycle, rearrange, flow into new patterns. Nothing is permanent except the elements themselves, constant in their essential nature even as they take countless forms. Phosphorus, element 15, glows in the dark. White phosphorus, exposed to air, oxidizes slowly and emits a faint greenish-white glow, what alchemists called cold light. Phosphorus is essential for life, found in DNA and RNA, in ATP molecules that store and transfer energy in cells, in bones and teeth. The phosphorus cycle is slower than carbon or nitrogen cycles, with phosphorus moving from rocks to soil to living things over geological timescales. Eventually, phosphorus washes into the ocean, where it can be locked in sediments for millions of years before geological processes return it to land. There's a patience in phosphorus, a reminder that not all cycles operate on timescales we can perceive. Some processes unfold over millions of years, and that's exactly as long as they need to take. Sulfur, element 16, has been known since ancient times, found in volcanic regions, bright yellow crystals that smell like rotten eggs when heated. Sulfur is essential for proteins, creating the bonds that help proteins fold into their functional shapes. Without sulfur, proteins couldn't maintain their three-dimensional structures, and life as we know it couldn't exist. Sulfur also plays roles in metabolism, in detoxification processes in your liver, in the keratin that makes up your hair and nails. Some of the earliest metabolic pathways evolution discovered used sulfur compounds, processes that still occur in bacteria around deep-sea hydrothermal vents, where superheated water rich in sulfur compounds erupts from the ocean floor. These environments might resemble the conditions where life first began. Sulfur connects us to the deepest past, to the very origins of biology. Chlorine, element 17, is a yellow-green gas that's toxic to breathe, yet in controlled amounts, chlorine compounds purify water, making it safe to drink. The chloride ion is essential for life, helping regulate fluid balance and playing roles in digestion and nerve function. This duality, dangerous in one form and essential in another, appears repeatedly in the periodic table. It reminds us that danger and safety aren't inherent properties but relationships, contexts, concentrations. Chlorine in swimming pools has a distinctive smell that evokes summer, childhood, leisure. That scent is actually chloramine, created when chlorine reacts with organic matter. Even in our leisure, chemistry is at work, invisible processes maintaining the conditions we need to play safely in water. Argon, element 18, is another noble gas, making up about 1% of the atmosphere. Right now, with every breath, you're inhaling argon atoms that do absolutely nothing in your body. They enter your lungs, pass through your bloodstream, return to your lungs, and get exhaled, completely unchanged. Argon is used in light bulbs and welding because it's so inert. Nothing reacts with it. It doesn't burn, doesn't corrode, doesn't interact. There's something peacefully neutral about argon, a presence without interference. As you breathe, argon is there, along for the ride, neither helping nor harming, just present. Sometimes presence is enough. Not everything needs to react, to change, to do. Sometimes simply being, simply existing, is a valid state. We've now completed the first 18 elements, the first 3 periods of the periodic table. These elements make up the vast majority of Earth's crust and atmosphere, the foundation of the world we know. As we continue our journey, the elements become less familiar, more specialized, but no less important in the grand design. Let your breathing slow even more. Feel the weight of your body supported completely by what lies beneath you. The elements that form your bed, your pillow, your blanket, all are from the periodic table, arranged in useful ways. Even your rest is supported by chemistry, by the reliable properties of matter. Potassium, element 19, is so reactive it must be stored in oil, like sodium. Yet potassium ions are crucial for heart function, for muscle contraction, for nerve signals. Your heart beats because of electrical signals created by potassium and sodium ions flowing across cell membranes. The rhythm of your heartbeat, steady and reliable, depends on the properties of these elements, their charges, their sizes, their tendencies to move through protein channels. Potassium-rich foods like bananas, sweet potatoes, and spinach help maintain this balance. The potassium in a banana today might have been in soil last year, in rock decades ago, in ancient ocean sediments before that. Everything cycles. Nothing is truly consumed, only borrowed and returned. Calcium, element 20, builds bones and teeth, making up about 2% of your body weight. The skeleton that supports you, that lets you stand and move, is primarily calcium phosphate, a mineral called hydroxyapatite. Your bones are alive, constantly being dissolved and rebuilt, with cells called osteoclasts breaking down bone and osteoblasts building new bone. Over the course of about 10 years, your entire skeleton is replaced, calcium atom by calcium atom. You are not the same physical structure you were a decade ago. The atoms have been replaced, yet the pattern continues, the information of your form maintained even as the material substance changes. This is deeply meditative. We are patterns, not things. The elements flow through us, and we persist as the pattern they temporarily form. Calcium ions also trigger muscle contraction and play roles in cell signaling. The influx of calcium into a cell can trigger cascades of responses. In neurons, calcium helps regulate neurotransmitter release. Every thought involves calcium. As you drift into sleep, calcium is there, enabling the neural processes that allow consciousness to shift into different states, that allow dreams to form, that allow restoration and memory consolidation to occur. Calcium is an element of structure and signals, of stability and communication. Scandium, element 21, is the first of the transition metals, elements that occupy the middle block of the periodic table. Scandium is relatively rare and mostly used in specialized alloys. It doesn't have a vital biological role that we know of. Yet scandium exists, has its place in the table, formed like all elements heavier than hydrogen and helium inside stars. Every element has value in the cosmic sense, each representing a particular arrangement of protons that creates unique properties. Not everything must be common or biologically essential to have worth. Scandium reminds us that existence itself is enough. The periodic table has room for everyone, common and rare, reactive and inert, essential and specialized. Titanium, element 22, is strong, lightweight, and highly resistant to corrosion. Titanium doesn't react with body tissues, making it ideal for medical implants, for replacement joints, for dental implants. People carry titanium inside their bodies, integrated peacefully with bone and tissue. This element became part of them, helped them move without pain, chew food, live better. Titanium is also used in aircraft, in spacecraft, in applications where strength-to-weight ratio matters. The white pigment in paint is often titanium dioxide, brightening walls, creating the backdrop of our interior spaces. Titanium is an element of integration, of strength that doesn't overwhelm, of compatibility with living systems. Vanadium, element 23, was named after Vanitas, a Norse goddess, because its compounds display such beautiful colors: green, blue, yellow, orange, red. The same element producing different colors depending on its oxidation state shows chemistry's aesthetic dimension. Beauty emerges from electron arrangements, from how atoms absorb and reflect light. Vanadium is used in steel alloys to increase strength and is also found in some organisms, where it plays roles in enzyme function. The fact that living things have found uses for obscure elements like vanadium speaks to life's creativity, its ability to work with whatever is available, to find purpose in the full palette of the periodic table. Chromium, element 24, gives rubies their red color and emeralds their green, depending on its oxidation state and what it's combined with. The name chromium comes from the Greek word for color. Chromium compounds were used in pigments, creating vibrant yellows and oranges and greens in paintings. Artists unknowingly worked with elements, arranging atoms to capture light in particular ways, creating works that would last for centuries because the pigments, the elements themselves, remain stable. Chromium is also used in stainless steel, preventing rust and corrosion. Your kitchen sink, your utensils, might contain chromium, quiet and unnoticed, preventing oxidation, maintaining shine. Chromium is an element of preservation and beauty, of resisting decay. Manganese, element 25, is essential for photosynthesis, helping chloroplasts split water molecules to release oxygen. Without manganese, plants couldn't produce oxygen, and the atmosphere you depend on wouldn't exist in its current form. Manganese also plays roles in bone formation, blood clotting, and metabolism. It's found in nuts, whole grains, leafy vegetables. The manganese in your body helps your cells generate energy, protect against oxidative damage, build connective tissue. Like many trace elements, manganese is needed in small amounts but is absolutely essential. This teaches us something about balance, about how even tiny quantities can be critical. Not everything that matters is abundant. Sometimes the smallest presences have the largest impacts. Iron, element 26, sits at the heart of hemoglobin, the protein in red blood cells that carries oxygen through your body. The iron atom in hemoglobin binds oxygen in your lungs and releases it in your tissues, a perfect molecular delivery system. The iron in your blood gives it its red color. You are, quite literally, powered by iron. Most of Earth's core is molten iron, generating the magnetic field that protects our planet from solar radiation. Iron is also the endpoint of fusion in massive stars. Stars can fuse lighter elements and release energy, building heavier elements, but iron is where this process reaches its limit. Fusing iron requires energy rather than releasing it. When a massive star's core turns to iron, it can no longer support itself, and the star collapses, triggering a supernova. All elements heavier than iron in the periodic table were created in these supernova explosions or in collisions between neutron stars. The iron in your blood came from such explosions. You carry the remnants of stellar death inside you, repurposed for life. There's poetry in that, a cycle of destruction and creation, of death giving rise to new forms. Iron connects us to the most violent events in the cosmos, yet in your body it performs the gentle task of carrying oxygen, enabling the quiet burning that keeps you alive. As you sink deeper into sleep, feel gratitude for iron, for the stellar explosions that made it, for the billions of years of cosmic evolution that arranged these elements into you. Cobalt, element 27, is essential for vitamin B12, the only vitamin that contains a metal atom. Vitamin B12 is crucial for nerve function, for DNA synthesis, for red blood cell formation. Cobalt sits at the center of B12's complex structure, a single atom around which the rest of the molecule is arranged. Without cobalt, we couldn't make B12, and our nervous systems would degrade. Cobalt is also used in alloys, giving tools hardness and heat resistance. Blue pigments in glass and ceramics often contain cobalt, a color that has decorated human creations for thousands of years. Cobalt blue has a depth, a richness, that has captivated artists and craftspeople across cultures and eras. The same element that maintains your nerves also creates beauty in art. Nickel, element 28, is found in Earth's core along with iron, and in many enzymes, particularly those in bacteria. Some bacteria use nickel-containing enzymes to metabolize hydrogen or carbon monoxide, surviving in environments that would kill most life. Nickel is also used in coins, in alloys, in rechargeable batteries. The name nickel comes from the German word for devil or demon, because miners found it frustrating that nickel ore looked valuable but couldn't easily be smelted like copper. This reminds us that human perception isn't always accurate, that something dismissed as worthless in one era can become essential in another. Nickel, once cursed by miners, now enables technologies they couldn't have imagined. Copper, element 20 Nix, has been used by humans for over 10,000 years. Copper was one of the first metals we learned to extract from ore and shape into tools and ornaments. The Statue of Liberty is covered in copper, now turned green by oxidation, copper oxide and copper carbonate, creating that distinctive patina. Copper is an excellent conductor of electricity, used in wiring throughout modern buildings. The electrical signals traveling through copper wires power lights, computers, refrigerators, the entire infrastructure of modern life. Copper is also essential for life, playing roles in numerous enzymes, in electron transport chains in mitochondria, in collagen formation. The same element that carries electricity through wires also carries electrons in your cells, enabling the processes that generate energy from food. Zinc, element 30, is the final element we'll explore in detail on this journey through the periodic table. Zinc is essential for immune function, wound healing, DNA synthesis, and cell division. Zinc fingers are structures in proteins where zinc ions help proteins bind to DNA, regulating which genes are turned on or off. Your body needs zinc to maintain the very instructions that make you yourself, to read and implement the genetic code written in your DNA. Zinc is also used in galvanizing steel, protecting it from rust, and in alloys like brass. The golden color of brass instruments, of doorknobs and decorative hardware, comes from the copper-zinc alloy. Zinc is an element of protection and regulation, helping maintain boundaries and control processes. As we reach zinc, element 30, we've journeyed through the essential elements that make up most of the world around us and within us. Beyond zinc, the periodic table continues, elements becoming increasingly rare, more specialized, more exotic. There's gallium, which melts in your hand. There's selenium, essential in tiny amounts. There's bromine, the only non-metal that's liquid at room temperature. There's krypton and xenon, more noble gases. There's silver and gold, precious metals humans have valued for millennia. There's tin and lead, molybdenum and palladium, each with its properties, its uses, its place in the grand design. The periodic table continues through all 94 naturally occurring elements, up to uranium and beyond, into elements that must be created artificially in laboratories and nuclear reactors, elements that exist for only fractions of a second before decaying into lighter elements. These super-heavy elements at the bottom of the periodic table push the boundaries of matter itself, exploring what arrangements of protons and neutrons are even possible. They remind us that reality has edges, limits, that not everything conceivable can exist. Yet what does exist is remarkable enough. From hydrogen to uranium, these 94 natural elements combine in countless ways to create everything: stars and planets, oceans and atmosphere, rocks and living things, consciousness and thought. The elements are not alive, yet they enable life. They have no intentions, yet their properties determine what is possible. The periodic table is a map of possibility, showing what matter can do when arranged in different patterns. It's a profound achievement of human understanding, taking the complexity of the material world and organizing it into rows and columns that reveal deep patterns, that predict properties, that make sense of nature's diversity. Why is the periodic table calming to contemplate? Perhaps because it represents order and chaos, pattern and randomness, predictability in a confusing world. The periodic table doesn't change based on opinion, politics, fashion, or mood. It simply is. These elements have been here since stars first formed them, and they'll be here long after we're gone. There's peace in that permanence, in that reliability. The universe has rules, deep regularities that hold true regardless of circumstance. Perhaps it's calming because the periodic table shows us that complexity emerges from simplicity. Just protons, neutrons, and electrons, arranged in different numbers, create all the diversity of matter. You don't need endless fundamental particles or mysterious forces. Just these few simple pieces, following straightforward rules, generate everything. This suggests that understanding is possible, that beneath complexity lies comprehensible order. The universe isn't arbitrary or capricious. It follows laws we can discover and describe. Perhaps it's calming because contemplating the periodic table connects us to something larger than ourselves. The elements link us to stars, to deep time, to the entire cosmos. We are made of stardust arranged into temporarily complex patterns. We are the universe experiencing itself. This perspective can make daily worries seem smaller, less urgent. On cosmic timescales, our troubles are momentary fluctuations. The elements endure. The patterns hold. The universe continues its slow, patient processes, building complexity, creating conditions for stars and planets and life to emerge, then eventually breaking everything down again, recycling everything, beginning anew. The elements teach us about cycles, about change and continuity. Individual atoms persist essentially forever, but the forms they take are temporary. Your body constantly exchanges atoms with the environment. You breathe out carbon dioxide that plants will absorb. You shed skin cells that break down into elements that enter soil and water. You consume food, breaking down complex molecules into simpler ones, rearranging those atoms into your own structures. Nothing you are is permanent in its current form, yet the elements that compose you are eternal. You are a pattern in the river of matter, a temporary eddy in the flow of atoms through time and space. This understanding can bring acceptance, can ease the fear of change and impermanence. If we are patterns rather than things, then change is natural, inevitable, even desirable. Patterns can persist even as their component parts are replaced. The pattern of a river remains even though the water is constantly flowing, never the same molecules from moment to moment. You are like that river, a continuity of pattern even as the substance constantly changes. This is not dissolution but participation in something larger, a great cycling and recycling that has continued since the beginning and will continue until the end. The periodic table also teaches us about relationship and context. Elements aren't good or bad in themselves. Chlorine is toxic as a gas but essential as chloride ions. Sodium reacts violently with water but is crucial for nerve function. What matters is how elements are arranged, what they're bonded to, what concentration they're in. This is true beyond chemistry. Context and relationship determine meaning and value. The same thing can be harmful or helpful depending on circumstance. This suggests a way of being in the world, flexible, contextual, aware of relationships rather than fixated on isolated properties. As you lie here, hovering between waking and sleeping, you are participating in chemistry. Your brain is using glucose and oxygen in controlled reactions that release energy. Ions are flowing across membranes, creating the electrical activity that generates consciousness. Neurotransmitters are being released and absorbed, modulating your mental state. Melatonin, a molecule built from carbon, hydrogen, nitrogen, and oxygen, is helping your brain transition into sleep. All of this happens automatically, elements and molecules following their tendencies, obeying the laws of chemistry, creating the conditions for consciousness to rest and restore itself. You don't have to control this process, understand it completely, or make it happen. It happens on its own, a gift from the elements, from the long history of evolution that learned to harness their properties, from the structure of reality itself. You can trust these processes, let go into them, allow the chemistry of sleep to take over. Your body knows what to do. The elements know their roles. Everything is proceeding according to pattern, ancient and reliable. In some real sense, there is no separation between you and the rest of the universe. The elements in your body are the same elements in the air, the earth, the stars. The carbon breathing out of you will be absorbed by plants. The water you drink contains hydrogen and oxygen that have circulated through Earth's systems for billions of years. You are not a separate, isolated thing but a process, a temporary concentration of elements that are constantly flowing, cycling, participating in planetary and cosmic patterns. This isn't loss of self but expansion of self, recognition that self was never as separate or bounded as it seemed. The periodic table shows us that everything is connected. Elements were made in stars, distributed by supernovas, gathered into planets, cycled through geological processes, taken up by living things, returned to the environment, over and over in endless cycles. There is no waste in nature, only transformation. What seems like an ending is always a beginning of something else. The carbon dioxide you exhale feeds plants. The water you release returns to the hydrological cycle. The elements that compose you will eventually return to earth, to air, to water, becoming part of other patterns, other temporary arrangements, other stories. This is the great lesson of the periodic table. Nothing is truly lost, only transformed. Energy and matter are conserved. They change form but persist. This can bring comfort when contemplating change, loss, endings. What ends in one form continues in another. The elements remember nothing, carry no grief, simply flow from pattern to pattern, eternally present, eternally available for new arrangements. They are the universe's way of exploring all possibilities, of creating temporary complexity and beauty before dissolving back into simplicity, then creating again. As you drift deeper now, let yourself become like the elements. Let go of holding any particular form too tightly. You are a pattern, and patterns can shift, flow, dissolve, and reform. In sleep, consciousness loosens its grip on identity, allows the boundaries to soften, permits the mind to wander through strange territories where the usual rules don't apply. This is healing. This is necessary. The brain needs to release its daytime structures, to process and integrate experiences, to restore chemical balances, to repair cellular damage. Sleep is a return to a more elemental state, where the complex organization of waking consciousness can temporarily dissolve. Let us continue our journey now through the elements, moving beyond the first 30 into the richer territories of the periodic table, where metals become more specialized, where rare elements reveal their unique properties, where the story of matter becomes more intricate and beautiful. Gallium, element 31, has a delightfully strange property. It melts at just slightly above room temperature, around 30 degrees Celsius. You can hold a piece of gallium in your hand and watch it slowly turn to liquid, pooling in your palm, silvery and strange. Gallium was predicted to exist before it was discovered. Dmitri Mendeleev, who organized the first widely recognized periodic table in the 19th century, noticed gaps in his arrangement and predicted the properties of missing elements. When gallium was discovered, its properties matched Mendeleev's predictions almost exactly. This was one of the great triumphs of the periodic table, showing that the pattern was real, that understanding the organization of elements could predict undiscovered ones. Gallium is used in semiconductors, in LEDs, in solar panels. The light from energy-efficient bulbs often depends on gallium compounds. Every time you turn on an LED light, you're using gallium's unique electronic properties, its ability to emit light when electricity passes through it. Gallium teaches us about prediction and confirmation, about how patterns can reveal hidden truths, about how the universe is more knowable than it might seem. When we understand deep patterns, we can see beyond what's immediately visible to what must exist. Germanium, element 32, was another element predicted by Mendeleev before its discovery. He called it EKA silicon and predicted its atomic weight, density, and chemical properties. When germanium was discovered, Mendeleev's predictions were confirmed, further validating the periodic table's organization. Germanium was used in early transistors before silicon became the standard. The first transistor radios, the first electronic devices that began the digital revolution, used germanium. Though silicon later proved more practical, germanium played a crucial role in the birth of our technological age. Sometimes elements are important not for their ultimate dominance but for showing what's possible, for opening doors that others walk through. Germanium reminds us that all contributions matter, even those that are later superseded. Progress builds on what came before. The foundations don't disappear just because new structures rise above them. They remain, supporting everything that follows, enabling what would otherwise be impossible. As you rest here, consider how your own life builds on countless predecessors, how you are supported by layers of history, by efforts and discoveries and sacrifices made by people you'll never know, all of it accumulated, all of it lifting you higher than you could reach alone. Arsenic, element 33, is famous as a poison, yet in tiny amounts it may play biological roles we don't fully understand. Some organisms can use arsenic in place of phosphorus under extreme conditions. Life is more flexible than we sometimes assume, more creative in working with available resources. Arsenic compounds were once used in medicines, in pigments, in pesticides. The bright green wallpaper in Victorian homes sometimes contained arsenic, slowly releasing toxic gas as the pigment degraded. Beautiful and deadly, arsenic reminds us that appearance and reality can diverge, that what seems attractive can harbor danger. Yet even arsenic has its place in the periodic table, its role in the cosmic inventory of matter. No element is wholly evil or wholly good. Context and dose determine outcome. This is a principle worth remembering. Complexity resists simple judgments. Most things are neither entirely beneficial nor entirely harmful but exist in relationship, in balance, in specific contexts that determine their effects. Wisdom lies in understanding these relationships rather than making blanket pronouncements. Selenium, element 34, is essential for life in small amounts but toxic in larger quantities. Selenium is part of several important enzymes, including ones that protect cells from oxidative damage. Too little selenium causes health problems. Too much causes poisoning. There's a narrow window where selenium is beneficial, a reminder that balance is everything. More isn't always better. The optimal amount is often somewhere in the middle, not too much, not too little, but just right. This Goldilocks principle applies to many things beyond chemistry. We need the right amount of stimulation, of rest, of challenge, of ease. Finding that balance is an art, a practice of paying attention and adjusting constantly. Selenium was named after Selene, the Greek moon goddess, because it was discovered soon after the element tellurium, which was named after the earth. Moon and earth, pair elements, reflecting ancient mythological relationships in modern chemistry. The names we give things carry history, carry metaphor, carry associations that color how we think about them. Even in science, we can't escape story, can't escape the human need to connect new knowledge to existing patterns of meaning. Bromine, element 35, is one of only 2 elements that's liquid at room temperature. Mercury is the other. Bromine is a dense, reddish-brown liquid that evaporates easily, creating a choking vapor. The name comes from the Greek word for stench. Bromine compounds are used in flame retardants, in water purification, in photography. The ocean contains bromide ions naturally, part of the complex mixture of dissolved salts that gives seawater its chemistry. When you swim in the ocean, you're immersed in a solution containing traces of dozens of elements, a reminder that the sea is not just water but a rich chemical environment, a medium that enabled life to first evolve, a womb from which all terrestrial life eventually emerged. Bromine connects us to the ocean, to the ancient seas where life began, to the saline environment that our cells still carry within them. Your blood has a salt concentration similar to ancient seawater, a memory of our marine origins. We carry the ocean inside us, a tiny enclosed sea that bathes our cells, maintains the chemical conditions that life requires. You are not just on the earth but are part of it, continuous with it, an extension of geological and oceanic processes into the realm of biology and consciousness. Krypton, element 36, is another noble gas, heavier than helium, neon, or argon. Krypton is used in high-performance light bulbs, in lasers, in some types of photography. The name comes from the Greek word for hidden, because krypton was difficult to discover, present in the atmosphere in tiny amounts, requiring careful fractional distillation to isolate. Many rare elements were hidden for centuries, not because they didn't exist but because we lacked the techniques to detect them. This reminds us that absence of evidence isn't evidence of absence. Just because we can't see something doesn't mean it isn't there. Reality often contains more than we can currently perceive. Krypton's most famous association might be with Superman, whose home planet was called Krypton, and kryptonite, the fictional substance that weakens him. Even fictional stories incorporate elements from the periodic table, using their names to add scientific flavor, to anchor fantasy in the real world just enough to make it believable. Chemistry provides a language, a set of concepts, that permeates culture, shows up in unexpected places, connects science to storytelling. Rubidium, element 37, is a soft, silvery metal that ignites spontaneously in air and reacts explosively with water. It must be stored very carefully, under inert conditions. Yet rubidium has legitimate uses. It's used in atomic clocks, taking advantage of the precise frequencies at which rubidium atoms absorb electromagnetic radiation. These atomic clocks are extraordinarily accurate, losing less than a second over millions of years. The most accurate timekeeping humanity has achieved depends on the quantum properties of elements like rubidium and cesium. Time itself, as we measure it, is defined by atomic transitions, by the reliable behavior of electrons in specific elements. Rubidium teaches us about precision, about how the very nature of elements, their quantum structure, their energy levels, provides natural standards, reliable reference points that don't change. The universe has built-in rulers and clocks, patterns we can discover and use to measure reality with extraordinary accuracy. This precision emerges from simplicity, from the basic structure of atoms obeying quantum mechanics. Deep understanding reveals deep order. Strontium, element 38, is famous for its radioactive isotope, strontium-90, a dangerous component of nuclear fallout. When strontium-90 is ingested, it concentrates in bones, where it can cause cancer over time. The body mistakes strontium for calcium because they're chemically similar, both being alkaline earth metals in the same column of the periodic table. This similarity in chemical properties, arising from similar electron configurations, can be deadly when the isotope is radioactive. Yet stable strontium isn't particularly dangerous. Strontium compounds produce brilliant red colors in fireworks, part of the palette of colors that light up the night sky during celebrations. Strontium reminds us that elements can have both beneficial and harmful isotopes, that the number of neutrons matters as much as the number of protons. Two atoms with the same number of protons are the same element, but different numbers of neutrons create different isotopes with different stabilities, different radioactivities, different behaviors. Chemistry and nuclear physics intertwine, showing that the full story of matter requires understanding both electronic structure and nuclear structure. Yttrium, element 39, is part of a complex story of interwoven elements. The village of Ytterby in Sweden is the source of rocks that yielded not just yttrium but also ytterbium, erbium, and terbium, for elements named after one small town. This speaks to how elements often occur together in nature, how similar chemical properties cause them to concentrate in the same minerals. Yttrium is used in high-temperature superconductors, in LEDs, in cancer treatment. It's one of many elements that most people have never heard of but that play crucial roles in modern technology and medicine. The rare earth elements, of which yttrium is often grouped with despite not technically being one, are essential for smartphones, computers, electric vehicles, wind turbines, the entire infrastructure of renewable energy and digital technology. These elements were once considered laboratory curiosities, interesting but not particularly useful. Now they're strategic resources, critical for the technological civilization we've built. This transformation from obscure to essential happened within a few decades, a reminder that we can't always predict what will become important, what knowledge will prove valuable. Basic research into the nature of matter, pursued for understanding rather than immediate application, creates the foundation for future technologies we can't yet imagine. Zirconium, element 40, is highly resistant to corrosion, making it valuable for nuclear reactor components, for chemical processing equipment, for medical implants. Zirconium oxide is used in dental crowns and in cubic zirconia, a diamond simulant. Something artificial, human-made, can be beautiful in its own right, not as a substitute for something else but as itself. Cubic zirconia has its own properties, its own aesthetic. It doesn't need to be diamond to have value. This is a lesson about authenticity. Things can be worthwhile on their own terms, not only in comparison to something else. Zirconium comes from the mineral zircon, which is also useful for dating rocks. Zircon crystals are extremely durable and can survive geological processes that destroy other minerals. Some zircon crystals are over 4 billion years old, nearly as old as Earth itself. These ancient crystals contain information about early Earth conditions, about the formation of continents, about the early presence of water. Matter remembers. Not in a conscious way, but through structure, through isotopic ratios, through inclusion patterns that record the conditions under which minerals formed. The rocks beneath our feet contain the history of the planet, written in the language of chemistry and physics, waiting to be read by those who understand the code. Niobium, element 41, is used in superconducting magnets, in steel alloys, in jewelry. Niobium can be anodized to produce beautiful colors, blues and purples and golds, colors that come from thin oxide layers that interfere with light. The color isn't a pigment but an optical effect, an interference pattern created by structure at a scale comparable to wavelengths of visible light. This is how butterfly wings create their iridescent colors, how oil slicks shimmer with rainbow patterns. Structure creates color, pattern creates beauty. This principle extends beyond the visible. Structure at all scales creates the properties we observe, from the quantum structure of atoms to the macroscopic structure of materials. Niobium was named after Niobe, a figure from Greek mythology who was turned to stone while weeping for her dead children. The mythological names of elements connect chemistry to ancient stories, to the human effort to make sense of the world through narrative. We've always told stories about the world, about the substances we find, about how things work. The periodic table is a new kind of story, one told in the language of science, but still a story, still an attempt to organize and explain, to find pattern and meaning in the complexity we observe. Molybdenum, element 42, is used in steel alloys to increase strength and temperature resistance. Molybdenum is also essential for many enzymes, including ones that process nitrogen and sulfur compounds. Some of the earliest forms of life may have used molybdenum in metabolic pathways, though whether molybdenum or other metals came first in the history of life remains debated. What's clear is that life didn't just evolve in a chemical environment but co-evolved with it, finding uses for available elements, incorporating them into biological structures and processes. Life is opportunistic, creative, constantly exploring what's possible with available resources. The fact that we need trace amounts of molybdenum, that our enzymes won't function without it, shows how deeply we're embedded in chemistry, how we're not separate from the periodic table but are expressions of it. Every element in your body is there for a reason, playing some role, enabling some process. You are a walking, thinking, feeling periodic table, a temporary arrangement of elements engaging in extraordinarily complex chemistry that somehow generates consciousness, experience, the sense of being someone, of existing in time, of maturing. Technetium, element 43, is the first element in the periodic table that has no stable isotopes. Every isotope of technetium is radioactive, decaying over time into other elements. For this reason, technetium doesn't occur naturally on Earth in significant amounts. Any primordial technetium has long since decayed. The technetium we use is artificially created in nuclear reactors or particle accelerators. Despite being synthetic, technetium has important medical uses. Technetium-99 is used in millions of medical imaging procedures each year, helping doctors diagnose conditions, see inside the body, locate tumors and injuries. Technetium shows us that artificial doesn't mean useless or inferior. Human-made elements and isotopes can be beneficial, can serve purposes, can be integrated into systems that help rather than harm. The dichotomy between natural and artificial is less meaningful than we might think. Everything is made of elements from the periodic table, whether arranged by geological processes or by human hands. Chemistry doesn't care about the origin, only about the structure and properties. Ruthenium, element 44, is another rare element, used in electronics, in alloys, as a catalyst in chemical processes. Ruthenium was named after Ruthenia, a Latin name for Russia, connecting this element to geography, to the place where its discoverer came from. Many elements bear geographic names: francium for France, germanium for Germany, polonium for Poland, americium for America. These names map human geography onto the periodic table, recording the history of who discovered what, where scientific work was done, what national identities mattered to scientists making these discoveries. There's something touching about this, the way scientists wanted to honor their homelands by naming elements after them. It shows that even in the pursuit of universal knowledge, personal and cultural identities matter, shape what we do and how we think about it. Science is a human activity, embedded in culture, in history, in all the messy particularity of human life. It's not separate from humanity but is one of humanity's greatest expressions, our collective effort to understand the universe we find ourselves in. Rhodium, element 45, is one of the rarest and most expensive elements, more valuable even than gold or platinum. Rhodium is used in catalytic converters in vehicles, helping convert harmful exhaust gases into less harmful substances. A tiny amount of rhodium can process the emissions from a car's engine over hundreds of thousands of miles, enabling chemical reactions that break down pollutants. This is catalysis, participating in a reaction, enabling it to occur, but not being consumed in the process. The catalyst emerges unchanged, ready to facilitate the same reaction again. Catalysis is a powerful principle, relevant beyond chemistry. Sometimes the most important contribution isn't to be transformed but to enable transformation in others, to make things possible without being depleted yourself. Teachers do this, parents do this, anyone who helps others grow while maintaining their own integrity and capacity. Rhodium, rare and precious, teaches us about the value of enabling others, of facilitating necessary changes through one's presence and properties rather than through self-sacrifice. Palladium, element 46, is fascinating for its ability to absorb hydrogen. Palladium can absorb up to 900 times its own volume of hydrogen gas, the hydrogen atoms fitting into spaces in palladium's crystal structure. This makes palladium useful for hydrogen storage and purification. Palladium is also used in catalytic converters, in electronics, in dentistry. The discovery that palladium absorbs hydrogen so readily sparked interest in the possibility of cold fusion, a controversial claim in the late 20th century that hydrogen could be induced to fuse into helium at room temperature in palladium. Though the cold fusion claims were ultimately not supported by evidence, the episode shows how unexpected properties of elements can inspire new ideas, new questions, new lines of research. Palladium reminds us that matter still holds surprises, that even well-known elements can behave in unexpected ways under the right conditions. Science is never finished. There's always more to discover, more to understand, more complexity hiding in what seemed simple. This is one of science's great lessons. The more we know, the more we realize how much we don't know. Each answer reveals new questions. The horizon of knowledge recedes as we approach it, always beckoning us forward. Silver, element 47, has been treasured for millennia, used in coins, jewelry, decorative objects, utensils. Silver is the most conductive element, both for electricity and for heat. Silver is also antimicrobial, killing bacteria on contact. Before antibiotics, silver compounds were used to prevent infection in wounds. Even today, silver is used in some medical dressings and in water purification systems. The antimicrobial properties arise from silver ions disrupting bacterial cell membranes and interfering with their metabolism. Silver's beauty and utility have made it valuable across cultures and throughout history. Silver objects from ancient civilizations have survived, have been treasured, have been passed down through generations. Silver doesn't corrode like iron or tarnish like copper. It maintains its integrity over time, though it does develop a patina, a darkening from reaction with sulfur compounds in air. This patina is often considered attractive, adding character and age to silver objects. Sometimes wear and age don't diminish beauty but enhance it, add depth and story, make objects more interesting rather than less. Silver teaches us about endurance, about how some things persist through time, how quality and beauty can outlast their creators, can carry meaning and memory forward into the future. The silver in an ancient coin has not changed. It's the same atoms, arranged in the same structure, waiting patiently through centuries for someone to hold it, to wonder about it, to connect across time through this persistent material. Cadmium, element 48, is toxic and is being phased out of many uses, but it has been important in rechargeable batteries, in pigments, in metal plating. Cadmium yellow was beloved by artists for its bright, warm color, used by Van Gogh and Monet. The same substance that creates beauty in paintings is harmful to living things, a reminder of chemistry's dual nature. Almost any substance can be helpful or harmful depending on context, concentration, exposure pathway. Water is essential, but you can drown in it. Oxygen keeps you alive, but too much damages tissues. Even sunlight, necessary for life, causes skin cancer with excessive exposure. This isn't a flaw in reality, but a feature of it. Effects depend on relationships, on dose, on context. Wisdom involves understanding these nuances, avoiding simplistic thinking that labels things as simply good or bad. The universe is more subtle than that, more interesting, more complex. Cadmium is dangerous in your body but beautiful in a painting, and both facts can be true simultaneously. Holding multiple truths at once, accepting complexity and ambiguity, is a mark of mature understanding. Indium, element 49, has the interesting property of being very soft, like lead. You can scratch it with your fingernail. Indium is used in touch screens, in solar panels, in LEDs, as part of transparent conducting coatings. When you touch your phone screen, you're interacting with a surface coated with indium tin oxide, an amazing material that conducts electricity while being transparent. This seems almost paradoxical, but it's possible because of how electrons behave in this particular arrangement of atoms. Materials can have combinations of properties that seem incompatible but actually coexist because of their specific atomic structure. Indium oxide gives us touch screens, allows us to interact with digital interfaces, connects us to information and to each other through devices that fit in our pockets. Technology changes society, changes how we live and think and relate. These changes are enabled by materials, by chemistry, by understanding elements and how to combine them into useful forms. The social consequences of technology trace back to materials science, to the periodic table, to the properties of elements. Everything is connected. Social change and scientific discovery and technological innovation form a web of cause and effect that's impossible to fully untangle. Tin, element 50, has been used by humans for thousands of years. Bronze is an alloy of copper and tin, and the Bronze Age marked a major transition in human civilization, enabling better tools, better weapons, new forms of art and craftsmanship. Tin prevented copper from being too soft, creating an alloy that was harder, more durable, more useful. This discovery happened independently in different cultures, showing that human ingenuity, given similar materials and needs, tends towards similar solutions. Tin is also used to coat steel and tin cans, protecting the steel from rust and the food from metallic contamination. The thin layer of tin provides a barrier, a protective interface between the food and the container. Tin is soft and malleable, easy to work with, non-toxic, perfect for this application. The humble tin can enable food preservation on a scale that transformed society, allowing people to store food for long periods, to transport it long distances, to feed armies and cities and expeditions to remote places. Sometimes simple technologies have profound effects. Antimony, element 51, was known to ancient civilizations, used in cosmetics, in medicines, in alloys. The name antimony may come from Greek words meaning not alone, because antimony is rarely found in pure form but usually combined with other elements. This etymology, though debated, points to a truth about elements in nature. They tend to associate, to bond, to form compounds rather than existing in isolation. Pure elements are often human creations, the result of deliberate separation and purification. Nature prefers mixtures, combinations, complexity. Antimony compounds are used in flame retardants, in semiconductors, in various alloys. Like many elements, antimony has both legitimate uses and toxic properties. The dose makes the poison, a principle attributed to Paracelsus, the Renaissance physician and alchemist. This principle is foundational in toxicology. Almost anything can be harmful in large enough amounts, and even poisonous substances may have therapeutic uses in carefully controlled doses. Context determines outcome. The same atoms that harm in one situation help in another. Tellurium, element 52, is named after the Latin word for earth. Tellurium is rare, used in alloys, in solar panels, in thermoelectric devices that convert heat directly into electricity. Tellurium compounds have an unfortunate property. They give people who handle them a persistent garlic-like breath odor, even in tiny amounts. This shows how sensitive our senses can be to certain substances, how chemistry affects not just our health but our perception, our experience of the world. Smell is chemistry, molecules reaching receptors in your nose, binding to proteins, triggering neural signals that your brain interprets as scent. Every smell you've ever experienced is molecules from objects entering your nose and interacting with receptors. The smell of bread baking, of flowers, of rain on dry soil, all are chemistry, specific molecules that plants or fungi or chemical reactions produce, that travel through air, that reach you and trigger sensory responses that connect to memory and emotion. Tellurium's garlic odor is chemistry too, a reminder that our subjective experiences have objective, material causes, that consciousness and matter are not separate realms but intimately connected. Iodine, element 53, is essential for thyroid function. Your thyroid gland concentrates iodine from your bloodstream and uses it to make thyroid hormones, which regulate metabolism throughout your body. Too little iodine causes goiter, an enlargement of the thyroid as it tries to capture every available iodine atom. This was once common in areas far from the ocean, where dietary iodine was scarce. The addition of iodine to table salt, a public health measure implemented in the early 20th century, largely eliminated this problem. Such a simple intervention, adding one element to salt, prevented enormous suffering. And so we arrive at the end of our journey through the elements, where we find ourselves not at an ending, but at a peaceful understanding. You've traveled with me through hydrogen's simplicity, through carbon's infinite creativity, through iron in your blood and calcium in your bones. Each element a thread in the tapestry of everything that exists. There's something deeply calming about the periodic table, isn't there? Perhaps it's because it reminds us that beneath all the chaos and complexity of life, there is order. A beautiful, elegant order that was here long before we arrived and will continue long after we're gone. The elements don't worry, don't rush, don't fear. They simply exist, following the quiet rules written into the fabric of the universe itself. Consider for a moment that every element in your body was once part of a star. The oxygen you breathe was forged in the heart of a dying sun billions of years ago. The nitrogen that makes up most of the air around you was created in stellar furnaces so hot they're beyond imagination. You are not just in the universe. You are made of the universe. Stardust, quite literally, contemplating itself. This thought alone can be so soothing. When we feel small or lost, the elements remind us that we are connected to everything. The same helium that fills party balloons exists in the sun. The same neon that lights city signs glows in distant nebulae. We are part of an ancient cosmic story, and that story is told through the periodic table. Let's think about why the predictability of elements brings such peace to the mind. In a world where so much feels uncertain, where emotions shift like weather and circumstances change like seasons, the elements remain constant. Sodium will always react with water. Gold will always resist tarnish. Copper will always turn green when exposed to air. This reliability, this steadfast nature, offers our minds an anchor. The brain craves patterns. It seeks order in chaos, and the periodic table is perhaps the most elegant pattern in all of nature. Mendeleev saw it first, arranged the elements by their properties, and found that they repeated in regular intervals. Like a cosmic rhythm, a heartbeat of matter itself. Groups and periods, families of elements that share traits, sitting in neat rows that make sense. This pattern speaks to something deep in our consciousness, something that says, all is as it should be. Think of the noble gases, sitting serenely in the far right column of the table. Helium, neon, argon, krypton, xenon, radon. They don't react, don't bond, don't seek to change. They are complete unto themselves, content in their electron shells, perfect in their stability. There's a lesson in their calm independence. They remind us that sometimes, being still is enough. Sometimes, simply existing in our complete form is all that's required. And what of the metals that make up so much of the table? These elements that conduct heat and electricity, that bend without breaking, that can be shaped and reformed. They teach us about resilience, about conducting energy without being consumed by it, about flexibility in the face of pressure. Iron, the element at the core of the earth and in the center of your blood cells, strong yet workable, holding you up even as you drift into sleep. The halogens, so reactive and eager, sit just beside the noble gases. Fluorine, chlorine, bromine, iodine. They seek one electron to feel complete, reaching out to bond, to connect. They remind us of our own need for connection, but also that this seeking has its place in time. Now, as you rest, you need not reach or seek. Like the noble gases, you can simply be. Let's journey back to hydrogen for a moment, the first element, the simplest, the most abundant in the universe. One proton, one electron. In its purity, there is profound simplicity. Sometimes our minds grow tired from complexity, from trying to hold too many thoughts, juggle too many concerns. Hydrogen reminds us that we can return to simplicity. one breath, one moment, one peaceful thought at a time. The transition metals in the middle of the table create a sea of elements, each with its own character. Titanium, strong and light. Silver, precious and reflective. Nickel, reliable and versatile. They don't demand attention like the reactive elements at the edges. They exist in the middle ground, balanced and steady, neither too eager nor too withdrawn. This middle path, this balance, is where rest lives. Your cells store and release energy in perfect rhythm. ATP, the energy currency of life, carries phosphorus in its very structure. You need not think about it or control it. It simply works, billions of times per second, keeping you alive while you rest. How comforting to know that the elements within you know their roles, performing their quiet duties without supervision. Magnesium, element 12, plays a vital role in relaxation itself. It helps regulate neurotransmitters that calm the nervous system, helps muscles relax after contraction. The ancient Greeks discovered magnesium compounds in the region of Magnesia, never knowing how essential this element would prove to be for peace and rest. As you breathe slowly, magnesium is already there, helping your body remember how to let go. The lanthanides and actinides, those elements set apart at the bottom of the table, remind us that not everything fits neatly into expected places, and that's perfectly fine. Some elements need their own space, their own row, and they are no less important for it. Cerium in your phone screen, neodymium in your headphones, gadolinium in medical imaging. Each found its purpose, even set apart from the main table. As we near the end, think about the super heavy elements, those created in laboratories for mere moments before they decay. Oganesson, element 118, exists for less than a millisecond. Yet in that brief flash, it completes the table's 7th period, it fulfills a prediction, it proves that humans can touch the very edge of possible matter. These fleeting elements teach us that even brief existence has meaning, that duration is not the measure of significance. The periodic table ends, for now, at Oganesson, but theoretically, it could continue forever. Scientists imagine an island of stability somewhere beyond element 120, where new heavy elements might exist for longer. The table is not closed, not finished. It remains open to discovery, to expansion, to mystery. Like the universe itself, it hints at more beyond what we can see. And here's the final gift the elements offer our restless minds. They connect us across time and space. The carbon in your body was carbon in a plant, in an animal, in the air, in ancient seas, in the bodies of dinosaurs, in primordial Earth, in the stellar clouds before our sun was born. You are borrowing these atoms for a brief time. When you return them to the universe, they will become something else, someone else, somewhere else. Nothing is ever truly lost. Everything transforms, following the patient rules of chemistry, the gentle logic of the periodic table. So as you close your eyes, imagine yourself as a temporary arrangement of elements. A beautiful, complex, conscious pattern of atoms that has emerged for this moment to experience the universe. You are iron and carbon and oxygen and hydrogen, nitrogen and calcium and phosphorus and more. You are the universe experiencing itself, and for now, that universe is ready to rest. The elements continue their eternal dance, even in stillness. Electrons orbit nuclei in clouds of probability. Chemical bonds flex and form and break and reform. Energy transfers through your cells, guided by elemental wisdom older than Earth itself. You need do nothing but allow it. Allow the elements to be what they are. Allow yourself to be what you are. A peaceful collection of stardust, resting under starlight. The periodic table will be there tomorrow, unchanged, reliable, eternal in its patterns. Mendeleev's genius will still shine through those neat rows and columns. The elements will still tell their stories. But for now, those stories can wait. For now, there is only breath, and darkness, and the quiet knowledge that you are made of the same stuff as stars, and just like stars, you too deserve to rest in the vast, peaceful night of the cosmos. Sleep well, fellow stardust. The elements will keep watch while you dream. The periodic table will be there tomorrow, unchanged, reliable, eternal in its patterns. Mendeleev's genius will still shine through those neat rows and columns. The elements will still tell their stories of stars and supernovas, of Earth's formation and life's emergence, of everything that was and is and will be. But for now, those stories can wait. For now, there is only breath, and darkness, and the quiet knowledge that you are made of the same stuff as stars, and just like stars, you too deserve to rest in the vast, peaceful night of the cosmos. Think of the stars above you, even if you cannot see them. They're there, fusing hydrogen into helium, creating light and heat, synthesizing new elements in their cores. Someday, billions of years from now, our sun will create its final elements, will scatter them into space, and those atoms will drift in cosmic clouds until gravity draws them together into new stars, new planets, perhaps new life. The cycle continues, vast and patient and inevitable. You are part of that cycle. You are not separate from the universe, observing it from outside. You are the universe experiencing itself, a local arrangement of stardust that has become conscious enough to wonder about stardust. And that is perhaps the most calming thought of all. You belong here. You are made of exactly the right stuff, arranged in exactly the right way, for exactly this moment. Sleep well, fellow stardust. The elements will keep watch while you dream. They've been doing this work for billions of years. They know how to maintain a living system through the night. They know how to prepare you for morning. Trust in their ancient wisdom. Trust in the periodic table's perfect order. Trust that you are held by forces far older and stronger than worry, than fear, than any temporary trouble. The elements ask nothing of you now except permission to do what they do best, to simply be, to follow their nature, to carry you gently into sleep and through the night and back to morning. And you can give them that permission. You can let go, knowing that hydrogen and oxygen and carbon and all the rest will take care of the details while you rest in the vast, quiet peace of elemental night. Good night. Let the elements guide you home to sleep.